Hey everybody, Dr. A here, and in this video we're going to be providing some background information on how to use Castigliano's method for beams and frames. So let's go ahead and get started. Let's start with the first bullet point. What is Castigliano's method? Well, Castigliano's method in general is an energy-based method, and we use it to compute deformations. Now, if you watch some of my other content, we use Castigliano's method in some of my other videos to compute joint displacements of trusses. Well, here we're talking about flexure systems. Those are beams and frames. So in Castigliano's method, when we apply it to beams and frames, we're going to be interested in computing deflections, which we call delta, or slope angles, which we call theta, at a point on that type of flexure system, on the beam or the frame. Okay? Now, how do we do it? Well, similar to what we saw with trusses before, what we do is we place a variable load at the point of interest in the expected direction of deformation. Okay, now that variable load, what is it going to be? Well, it could either be a force or a moment variable load. Okay, now how do you know which one to use? Should you use a variable force or a variable moment? Well, that depends on what you're trying to compute. If you want to compute a deflection, delta, you're going to place a variable force P at the point of interest in the expected direction of deformation. If you are interested in a rotation angle or a slope angle theta, you're going to place a variable moment M prime. This is M prime, a little prime here, in order to compute that slope angle theta, okay? And you place that variable moment M prime at the point of interest in the expected direction of rotation on the system, all right? Now, this prime right here is just a label. This is not meant to be a derivative. M prime here is just used for the sake of labeling, okay? So what do we do next? We use the method of sections to compute internal moment functions for the entire system, all right? And then from there, we compute partial derivatives. Okay, now if you are calculating a delta, your partial derivatives are going to be the partial derivative of the moment function with respect to that variable load P. Now, if you were calculating a slope angle theta, the partial derivative will be the partial derivative of your moment functions with respect to the variable moment M prime. And you're going to do that for each of the domains of your problems. So if you have a multi-segment beam or frame where you have multiple abrupt changes, you're going to compute these partial derivatives on each of those domains, okay? And then last, we're going to apply Castigliano's formula, okay? Now, what does Castigliano's formula tell us to do? Well, let's write this down. If you want a deflection, Castigliano's formula is going to be equal to delta equals the summation as I goes from 1 to n of the integral from 0 to L m over EI times the partial derivative of moment with respect to force dx, and then all of that integral term is a sub I. Now, what does this mean? What are all these terms? Well, EI is the flexural rigidity on a segment I. L is the length of segment I. M is the internal moment function on segment I. And then dm dp is that partial derivative of the moment function with respect to the variable load P. And then the summation represents you adding up these integral terms for each domain you have, okay? Now, what if you want a rotation angle? Well, guess what? The rotation angle computation is almost the same. We're going to say theta equals the summation as I goes from 1 to n of the integral from 0 to L m over EI times the partial derivative d, but this time it's with respect to m prime, so it's dm prime dx sub I. Okay, so let's define these terms and write them all out, make sure we know what we're talking about. EI is the flexural rigidity, okay? N is the number of domains. Let me write that a little bit better. L sub I is the length of domain I. L sub I comes from this L, but you have this sub I term right here. I guess you could also say EI sub I as well. Flexural rigidity of domain I, just for the sake of completeness, okay? And then we already defined these partial derivatives, okay? Now, M is the internal moment function on domain I. So we can say, you know, M sub I is the internal moment function on domain I. Now, for the internal moment function on domain I, we're going to, when we take the integral, we're going to set the variable load, which is either P or M prime, to 0 for taking the integral. Okay, the reason why is because whenever you place this variable load, whether it's a moment or a force, on the system, you're going to have that P or M prime sprinkled inside of these moment functions. Now, when you take the integral of that, you need to set that P or M prime, whichever one it is, to 0, okay? Now, this brings me to another point, and this is where things are a little bit different compared to virtual work. So I'm going to put some stars here on this next point, okay? So for Castigliano's method, you can come up with different systems where you replace the real force with a variable force or couple moment, okay? In my videos and in my later examples, I'm not going to do that. What I'm going to do is I'm going to keep the real loads on the system with the variable load. All right, so if you recall, when we studied virtual work, we had two systems, right? We had a virtual system where we put a virtual unit load on the system and we took the real loads off. And then separately, we analyzed a real system, okay? With Castigliano's method, I like to use Castigliano's method by keeping the real loads and the variable load on one system together. So you do one type of system analysis. Now, there is an alternative version of this where you can replace the real forces or moments by those variable unit loads P or M prime, but I'm not going to cover that in my videos. Okay, so that's our background information on this, and we're be on the lookout for a couple of example videos right after this one. Thanks for watching.